Thank you. Awesome. Can everybody online hear us okay? We can't see you, so just someone speak up with a yay or a nay. I suppose a nay if you can't hear me.
Yes, we can hear you.
Okay, thank you. Thanks everybody for coming. My name is Chip Fletcher. I'm interim dean of the School of Ocean and Earth Science and Technology. I'm also a coastal geologist, a former professor, now an academic bureaucrat. But I've kept my hand in research, and my research team is known as the Climate Resilience Collaborative. And this is a group of very smart scientists who have been modeling various aspects of sea level rise, because as most people here know, sea level rise is causing types of flooding which are more than just waves coming over the shoreline. There's so much more complexity related to it. So the primary outlet of our research is a viewer, an online map viewer. Many of you use the Hawaii SLR viewer or sea level rise viewer, which is served by the PAC-IUS program, also here at the school. This viewer involves additional types of modeling, and we're now trotting it out for people to become familiar with as we expand the geographic scope of where our modeling has occurred. So I'll dive into all that here. Let me begin with a couple of slides about the topic of sea level rise. We've been monitoring the changing level of the ocean around the world for a couple of decades now. And we know without doubt that sea level is rising. This is the satellite altimetry record of rise. It's equivalent, the rate of rise over the last 30 some years is roughly 1 foot per century. But in the last decade, it has accelerated to about 1.5 feet per century and is continuing to accelerate. We know from the recent report from the Intergovernmental Panel on Climate Change, a series of reports came out beginning in 2021. The last report came out this past fall, 2023. 250 scientists agreed specifically to the wording that sea level is committed to rise for centuries to millennia due to continuing deep ocean warming and ice sheet melt, and will remain elevated for thousands of years. And they assign levels of confidence to the statements they make in these reports. And this statement, they assign high confidence. So this is a new condition for many planners and government agencies around the world to really begin to wrap our heads around. With continuing greenhouse gas emissions, we know that we're going to pass 1.5 degrees Celsius above the pre-industrial level. We almost reached it this year. And we are on track to warm, before the end of this century, 3 degrees Celsius above the pre-industrial level. And you can see that we're looking at 6 to perhaps as much as 20 feet of sea level rise that will play out over centuries and remain elevated for thousands of years. So this is a permanent and irreversible condition on our shoreline that we need to catch up to. Sea level has been rising for a century, slowly. We've seen it expressed in the form of chronic erosion, but it's now leaving that gentle rising phase, and it's going to be rapidly increasing the rate of rise. And our management programs are struggling to keep up with this problem. And so it's with this in mind that my research team is interested in modeling the impacts. Because there are so many different types of impacts, we're going to need to call on many different types of mitigation and adaptation. So here is a modeling result for 4 feet of sea level rise, which is an intermediate projection by the end of the century of annual wave run-up, typical summer swell in Eva Beach on the south shore of this island. Here is Dr. Shelley Habel measuring the salinity of the water table in Waikiki, which rises with sea level rise. If you have a well, just on the other side of the H1 here, down in the quarry area where our parking structure is, if you looked at the water table in a well down there, you would see it go up and down with the tides, meaning that as the ocean rises, the water table will rise permanently and irreversibly. We also see our drainage infrastructure, which is designed to work by gravity, becoming failing because as the ocean level rises, it's reaching zero elevation and gravity no longer works. And then when it rains, we have what's known as compound flooding. So these are all problems that hit our coastal communities, and all of our, or the vast majority of our communities in Hawaii are indeed coastal. Here is a erosion projection for 4 feet of sea level rise up in the Sunset area. So when will sea level reach different elevations in the future? This is a point of major uncertainty because we have portions of the Antarctic ice sheet that are retreating into the ocean in ways that we do not fully have a projection capacity. We don't fully understand the physics. And so a federal agency task force of scientists from NOAA, NASA, US Geological Survey, and the Army Corps put together planning scenarios for government agencies, community groups, and planners. And the bottom two scenarios here, this greenish one is the low scenario, the next one is the intermediate low scenario. In order for these scenarios to become true, sea level rise would actually have to slow down at this point. So we know that these are now irrelevant as we continue to emit greenhouse gases. And so we have then the intermediate and intermediate high scenarios, which modeled for the Honolulu tide gauge, take us basically to about 4 feet of sea level rise for the intermediate scenario by the end of the century, and about 6 feet of sea level rise for the intermediate high scenario. What scenario should we use for our planning? The answer is based on the sensitivity of the project. And for major expensive public infrastructure projects, a higher scenario should be used so that we don't get it wrong with regard to investing in a way that then becomes exposed to major flooding. And so this is the climate viewer that we're putting together. And it has several elements. I'm going to go through this quickly. The talks following me are going to break down the various types of modeling that are shown here. First, though, this whole viewer is modeled on the NOAA SLR viewer. It has the same elements. In fact, it takes the skeletal programming of that NOAA SLR viewer. So there's a slider bar here where we can raise and lower sea level rise. It's now set at 4 feet of sea level rise. And up here for timing, you can either have the intermediate or intermediate high scenario. So under the intermediate scenario, 4 feet of sea level rise occurs around 2100, the end of the century. Or under the intermediate high scenario, it would shift to about 21 or to 2080. There's the intermediate high. We shifted the time scale. So now it's a 4 feet of sea level rise would be around 2080. For further discussion of this, the City and County of Honolulu Climate Change Commission has a sea level rise guidance document, which dives into the questions related to this. So I want to walk through the elements on this viewer. We're going to focus in on Waikiki, Kaka'ako area. What you see here is what's known as passive flooding. This assumes the ocean is a flat, non-dynamic surface. Areas that lie at or below high tide at 4 feet of sea level rise would be flooded, and direct access by the ocean would be flooded in blue. Other areas that lie at or below high tide that are separated from the ocean by slightly higher topography are colored in green. One way to interpret the green is that it may be an area subject to groundwater flooding. And realizing this several years ago, we actually focused in on the question of modeling the water table. You can also turn on and off a satellite image. That's the same image, but with the satellite image turned on. It's easier to see without. And this is the groundwater model for 4 feet of sea level rise. Shelley has also recently introduced in the groundwater model portions of the water table that are less than a foot below the land surface, which are colored in dark orange. Am I right about that, Shelley? Dark orange, and portions of the water table that are 1 to 5 feet below the land surface are colored in light orange. So we know how soon we're going to be looking at the water table. And here in green is a model result for salt water coming out of our storm drains onto the streets and lands. This is called storm drain backflow. And we have a layer here from the city, which shows the individual drains in red dots that are going to be backflowing salt water. You can also click on the flooded area and see what the water depth is. This will be important for engineering solutions to this type of flooding. And here is a modeling result looking at the wave inundation. So we have Asaf Azuri will be talking about our modeling of wave inundation, and what's being modeled is an annual high wave. So just typical, in this case, South Shore summer swell. And that's shown in purple here. And of course, compound flooding. And Kayla Yamamoto will be talking about her modeling of a rainfall event, a Kona storm that occurred in December 2021. And so this shows the that event model result. You can combine all these into what I refer to as a dog's breakfast of colors and various types of flooding. That is the Slorexa, which I know we're all familiar with as a planning tool. That's available on this site, as well as a number of other layers that can be turned on and off, public infrastructure of various types, and planning layers of various types. We have a project focused on Ko'olaupoco, where we have also extended this modeling, a community resilience project under the auspices of the Office of Local Defense Community Cooperation, working with the Marine Corps base that we're going to be kicking off actually next week. And this is Waimanalo. Here you can see the location of cesspools in red dots, and some of the model results showing coastal erosion and other impacts. All right, winding up. So our modeling so far, we've modeled Ko'olaupoco. We've modeled the Kona district here on the South Shore. We're interested in moving next to Ko'olauloa and eventually around the island with community-based outreach efforts and this scientific modeling to underpin vulnerability assessments. And our talks that are coming up next, following me, will be a talk on vertical land motion and the improved viewer by Kyle Murray and Matt Barbie. Kayla will talk about compound flood modeling, Asaf about the wave flooding, Shelley about groundwater inundation. Chloe, one of our master's students, is going to talk about her modeling of the storm drain system in Waikiki. Anna and Rochelle are going to discuss the coastal erosion modeling. Christian and Aloha will go through our shoreline study web map where shoreline data is publicly available. And then Juliet will do a wrap up on our resiliency planning. And I was originally had an agenda item for 5 minutes, and I think I've taken 10 or even 15. So we're behind already, and I'll turn it over to whoever our next speaker is. Thank you very much.
All right, good morning, everybody. My name is Kyle Murray. I have a background in geophysics and geodesy, and I'm going to be talking kind of like a brief run through of my work on vertical land motion measuring for improved flood exposure modeling. So the basic level, we need at least 2 things to do a flood exposure model. An idea of the future sea levels over time, and then a measurement of the elevations of the coastal area. And so here's just an example. On the left, we have some future sea level rise projections from the IPCC. And on the right is a digital elevation model, or DEM. And so I guess the basic idea of flood exposure model is to simply identify the areas of that DEM that will be below sea level in the future, given some amount of sea level rise. And this is all under the assumption that the DEM is stable and it's not changing over time, and it acts as a good reference for flooding. So what I'm doing is kind of challenging that assumption by showing you that there is actual elevation change over time, and that should be taken into account. Okay, so we can kind of update this workflow by adding in measurements of elevation changes and then projecting that into the future with kind of updated DEMs, which can then be used to improve these types of flood exposure models. All right, so elevation change is also referred to as vertical land motion. It's most often observed as downward motion, which is land subsidence. So I'll be kind of referring to it as that. And it's really important to measure in coastal areas because it accelerates relative sea level rise. The main causes, I guess there are a lot of different causes for land subsidence, some of which I listed on the right over here. The main ones in Hawaii that we need to be concerned about from observations are sediment compaction and then volcanic activity. So how do we measure vertical land motion? We have pretty much 2 primary methods we use. And the first is continuous GNSS. These give you really dense temporal sampling and kind of point locations at specific locations on the Earth. And then another technique another technique is called INSAR. That stands for interferometric synthetic aperture radar. So this is a imaging satellite technique. It offers you really high resolution, dense spatial measurements, about weekly measurements. And these are relative measurements. The GPS or GNSS, these are very sparse along the coastlines of Hawaii. So my main focus is really in bringing in the INSAR imagery, which are relative measurements, and then referencing those to the more kind of absolute measurements of the GNSS network. Okay, so skipping ahead to kind of just like the results of some of these kind of data products. This is one of the main things I'm using, which is a map showing vertical land motion rates. So the red colors are subsidence rates. The more red, then that means it's subsiding more. And this is formed from basically thousands of differential images from multiple satellites over the course of about 10 years. So the result is really a detailed look at persistent subsidence features. And I know it's kind of difficult to see at this scale, so I'm gonna just zoom into one example area. This is the Mapuna area, the low-lying flood-prone area, kind of an industrial area, the South Shore. And again, this is showing in red the subsidence rates and millimeters per year. And this area is built up on a lot of artificial fill. So the likely cause of this subsidence is this long-term compaction and settling of those sediments over time. And not surprisingly, this area is already flooding regularly. And here are just a few images showing some of that during high tide days. Okay, so bringing this back into the workflow, how can we kind of use subsidence rates to update the flood exposure models? I want to just show you one way to visualize the outputs from that kind of model. This is a map, an animated map showing colors based on the decade when land will be below sea level in the future. So it kind of marches through those sea level rise projections and then plots it also on the map. So the red areas, for example, would represent areas that are probably already flooding regularly. And then the future kind of 100 years will be colored in blue. So the blue areas will be much later, but keep in mind, this is a very conservative estimate. This doesn't take into account any of the other factors that we know exacerbate climate or flooding and sea level rise issues. So let's see, you'll hear more about those in future presentations. So here's just another zoom into that Mapuna area to give you a more detailed look. And then finally, one of the questions we also have with this is how much does substance specifically contribute to these types of outputs from the model? And so the next map is just one way to visualize the specific contribution of subsidence to these outputs. And so this is now showing the colors are the number of years flooding is pushed earlier in time if we account for subsidence as opposed to not. And so these areas in red, if we don't account for subsidence, will be kind of on the order of several decades behind schedule if we're planning for these issues. So the main takeaway here is subsidence will really expand the area of flooding and accelerate the timeline that we have to prepare for it. And then I'll just hand it over to Matt. He's gonna give a quick run through of how we can maybe incorporate these into our viewers.
Great, thanks, Kyle. My name is Matthew Barbie. I kind of help manage data and then also come up with help manage the web app as well. So currently, as Chip showed you, we have a web viewer, web-based, and the existing one is very full. As you start to move through it, you realize there are a lot of options. There's a lot of data-driven options and a lot of ways to view data. But really, we're all viewing it on this computer screen and we have relatively limited real estate. And so it's going to be really one of the needs we've figured out is that we need to develop additional ways of viewing this data and working with the data and creating something useful for managers and decision makers to actually interact with this data. We have other data that we also plan to add to the viewer or develop a new viewer with, and that includes heat and addressing heat, drought, changes in precipitation, all of these ideas that we have that we want to model and bring into a viewer kind of area. So we want to explore those options to create a more dynamic experience or modeling interface. And of course, it's all going to restructure. So when you're talking about, like Kyle was, changing the DEMs, that's changing the basic assumption that your elevation data is static. It is not static. It is moving up and down. And then Kyle showed you how it moves down. And that affects every one of our model products. So that kind of begs the question, do we need a new viewer? And how do we focus that on the users, everyone in this room, but also the public? How do we want the public to interact with that? So one option is to allow sort of a dynamic interface with the elevation data, maybe building a tool that such as one in this case exists for the country of Denmark and many areas of Europe, where they actually allow you to interact with the elevation data, maybe even plan and put in things like dikes or retention basins and change the basic water flow in the equation. Our data would then be the backbone of this. It would provide all the information into that sort of interface. It would put the modeling there, it would put all of these layers and have them available. But then it would allow the user to actually say, hold on, we want to mitigate it this way. What are the impacts to the flow of water in this area? What is this? How does this actually look in plain view or in profile view? So that's sort of the next step. That's the next generation. We need to figure out how to build that, how to actually maybe work with folks in this room to figure out solutions on how to address some of these user interfaces, maybe in augmented reality, some sort of changes like that, where some of this can be tested in real life. So that's all I have. Thank you. And Kayla will come up next and speak about compound flooding.
Hi, everyone. I'm Kayla Yamamoto. I'm a climate modeling analyst for the CRC group, and today I'll be presenting on compound flood modeling using WRF hydro. So compound flooding Okay, compound flooding occurs when two or more flood drivers occur simultaneously or in close succession. And the combination of these multiple flood sources leads to greater impacts than when they occur on their own. And this is especially true for coastal urban communities where the threat of flooding seems to be coming from every direction. Some common coastal urban flood sources include rainfall runoff flooding. There are various marine inundation sources, groundwater inundation, and then also flooding due to storm drain backflow. And in Hawaii, these types of compound flood events are already happening for us. And with increasing sea level rise, we expect these events to become more frequent and more severe. So being able to better understand compound flooding and model it is essential for us to prepare for the future. And the way we do this is by using WRF hydro, which is a distributed physics-based hydrological model that allows us to simulate rainfall runoff flooding. We use two main components, which include the column land surface model shown in green. The schematic diagram on the right is showing the moisture and heat fluxes that are represented within this model. The main output here being surface runoff and infiltration excess. Next, we have the terrain routing module shown in blue. The overland flow module determines how water is routed on the surface, while the subsurface flow module determines how water moves laterally within the subsurface from column to column. And because we're interested in coastal urban applications, we have to use an extended version of WRF hydro called WRF hydro Kufa. WRF hydro Kufa expands on the original WRF hydro code by introducing two new model components. The first being a coastal boundary, which allows us to impose time and space bearing water levels along the coast to represent things like tides or storm surge. The second is stormwater drainage modeling, and this is done by coupling WRF hydro to the SWIM model. And Chloe O'Barrow will be presenting more on the SWIM model in her talk later today. Here's a figure from the paper that was published last year where they used this model to reproduce the flooding from Hurricane Irma. And for this presentation, we are looking at the coastal boundary. The static geographical inputs into the column land surface model include a digital elevation model along with land cover and soil texture data. The dynamic forcing inputs include meteorological data from the weather research and forecasting model, along with high-resolution precipitation data. And there's also water level data from the NOAA tide gauges. Specifically, we use the Honolulu tide gauge. Here's our model domain shown in blue. It covers the primary urban core, but we are mainly interested in the flooding that's occurring in this general Waikiki area. The event that we choose to validate our model is the December 2021 Kona storm. Here's a satellite imagery loop with the Hawaiian Islands circled in white, showing some of those high cloud tops and deep convective features in red and orange. Here's a closer look from the Molokai radar. The arrows pointing to the Waikiki area. You can see those deep convective cells in red and orange here passing over the model domain. And these features are associated with heavy rainfall. Using the NOAA Atlas 14 point precipitation frequency estimates, we're able to define this storm as a 50-year storm. And in addition, this storm, in addition to producing heavy rainfall, it also coincided with a king tide event. And you can also see from the plot that the verified water levels shown in green were noticeably higher than the predicted astronomical tide shown in blue. And this is due to the storm surge that was generated by the Kona low. Here's a video of our model output at the time of maximum flooding. On the right-hand side, we have some point observations that were used to help validate our model. So we're flying into the Manoa area, landing on Oahu Ave and East Manoa Road. From the first image on the right, you can see the flooding that was observed here. We were able to reproduce 4 inches of flooding. Next, we make our way over to the Iwalei substation, which was flooded. 3 transformers were reported to have failed, causing major power outages to much of downtown Honolulu. And here our model was able to reproduce 3 to 5 inches of flooding. Next, we make our way over to the Ward area over on Queen Street. From the second image on the right, you can see that significant flooding was observed in this area. And our model was able to reproduce 8 to 10 inches of flooding. Next, we have Alawai Neighborhood Park. From the third set of images on the right, you can see that there was flooding observed on the fields and along the courts and in the parking lot. And here our model was able to reproduce 4 to 6 inches of flooding. And then last, we make our way over to Kalakaua Ave. From the last image on the right, you can see that there was flooding observed on the main roads, spilling over into the side streets as well. And here our model was able to reproduce 4 to 6 inches of flooding. Here's a closer look at some of the flooding that was observed on Kalakaua Ave over in Waikiki. Next, we have a plot from the stream gauge located along the Manoa Pololo drainage canal. It's showing water levels in feet with respect to time. And in orange, we have the gauge height observations. And in blue, we have the model output. And what we can see is that our model is able to capture the tidal signals shown here, along with the combined effects of both the rainfall runoff and the tides. So once we're able to validate our model, one thing we can do is we can see how this flooding would change with increasing sea level rise. And one thing I want to point out is that these maps are showing us both floodwater depth and extent. So here the depth is represented with the change in colors, and the colors are shown in the legend on the bottom left there. And this makes these maps a useful tool for government planners and builders to help set guidelines for future development and infrastructure. So I'll start here with the original flooding, and I'll click through at 1 foot increments of sea level rise up to 4 feet. And what we're seeing as I'm clicking through is both the deepening and the spreading of the flooding. And so we've used our model here to investigate how the flooding from this 50-year storm event change with increasing sea level rise, but we can also apply this model to other sea level rise and storm scenarios in order to better assess and quantify future compound flooding events. And with that, I'll take any questions. Thanks.
Morning, everyone. My name is Asaf Azuri. I'm a physical oceanographer working here at UH at the Department of Oceanography. And Kiri also work with Chip Fletcher and his group, the CRC. And I'll be talking about wave-driven modeling of wave-driven phenomena that result in flooding. And I'll start by contrasting the existing modeling approach compared to the one that we have been employing these days for the CRC project. So what we see on the left is an example from the Silver Rise viewer for the annual high wave flooding. Now, the modeling done here involves cross-section that many cross-sectional lines that start from offshore location and go all the way on land. And the modeling is done along these lines. And later, the modeler interpolated to get this two-dimensional picture. Now, in this new approach, we're implementing a similar type of model, but it allows for full two-dimensional modeling. And we're therefore including a lot of physics that was missing in the wide-dimensional approach. For example, we allow for wave refraction, diffraction, and also wave-wave interactions, which leads to a generation of infragravity waves and other types of waves as well. Now, I want to show here an example of how the free surface output from the model looks like. This is for the Marine Corps base in Kaneohe Bay. You will see snapshots every 3 seconds. You see the waves are approaching the domain from the offshore boundary at some oblique incident angle. And also we can see that the model resolved the individual crests and troughs of these waves. And it allows for processes such as the one that I mentioned of refraction, diffraction, and wave-wave interactions, as well as others. Now, the first goal is to cover this with this modeling approach, all of the island of Oahu first, and then move to the remaining island. For Oahu, we started with Waikiki domain. You see here, that was the first domain we started with. We moved then to Waimanalo and Kaneohe, then to Hawaii Kai and Kaiwi. So pretty much all these southeasterly portion of the islands are covered. And now we start working on Hauula. So soon we'll have about half of the easterly half of the island covered. Now this modeling is done over a digital surface model, which includes the footprints of the building. And this is another enhancement on the previous approach that I mentioned earlier. And so it allows the water to move around all these obstacles, and the result is much more realistic. The modeling is done over a 5 meter by 5 meter grid, and then later on projected back onto the original 2 meter by 2 meter digital surface model grid. And I'll show you a few results from Waimanalo area. And the inset on the right is on the Marine Corps base. So this is with zero silver rise. And now I'll add 1 foot increment of silver rise. And again, this is with wave conditions that represent the annually recurring height, wave height. So 2 feet, 3, 4, and I'll stop at 5. We're going up to 10, but the results are quite dramatic. That's enough to show 5, which is representing the timeline that the chief presented earlier. And I'll end up with another example of result where I contrast the 3 versus 5 foot silver rise cases for Waikiki. And you can see here, this is an area of, this is the Hawaiian Hilton area. And this is with 3 foot. And now at the bottom, you'll see when you add 2 more feet to that, the results are quite different. You see the overall envelope of the flood went way further inland. And also, if you look more carefully, especially closer to the water-land interface, you'll see greater depth of the water flow. Now let's look at a different area of Waikiki, Kaka'ako, and Ala Moana. Again, this is the 3 foot. And adding 2 more feet and running the same kind of simulation, you'll see that there's much more coverage of the water further inland, and also the water depth are much greater everywhere along the coastline. Okay, I'll end with that. Thank you.
Aloha, everybody. Can you hear me? Hello, hello. Hi, I'm Shelley Habel. I'm a coastal hydrologist and coastal geologist for CRC. And mainly what I look at are inland sources of flooding from sea level rise. So not just the one we all think about, which is water coming up and over the shoreline, but also back through our storm drain systems and rising up beneath our feet from groundwater inundation. And so for our drainage systems, they've been designed to take stormwater from higher elevation drainage inlets and transport them under the force of gravity to drainage outlets or receiving waters, which in our case is the ocean. And so as sea level rises, it rises above those different components and it causes the drainage system to fail in phases. And the first is when the ocean level comes up and above the drainage outlet, followed by when we get rain, that water will back up through our drainage systems. And then the final phase is when it floods regardless of rainfall. And so under blue sky conditions, we get another source of flooding. So it's kind of like a double whammy, because not only are these drainage systems failing at transporting our storm water, causing that source of flooding, but it's adding an additional source of flooding, which is salty and corrosive. And then we have groundwater inundation. And so as sea level rises, a few things happen. One is that the water table rises, gets higher, and so that leaves less and less space between the ground surface and the surface of the water table. And so that's less space for our underground infrastructure. And so that starts to get submerged and corrodes a little faster. And then another thing that happens is that in places that are really low lying, that water table will come up and start to emerge, cause that source of flooding. And then because of saltwater intrusion, that water becomes saltier and saltier as sea level rises and more corrosive. And so we're already starting to experience the impacts of groundwater inundation in our really low-lying areas. This is in Waikiki, where the groundwater table, it's really not that far down below the ground surface. And Chip showed this earlier, but that's me in a basement taking up in the left-hand corner. That's me taking a picture, or me taking a measurement of the amount of salt in the water. And what I'm finding is that that groundwater is pretty much as salty as the ocean water itself, which is very, very corrosive. And it speeds up that corrosion of our underground infrastructure, where we're not really paying attention as much as we should be. Okay. And so just recently, we put out a review paper where we go through the various impacts of this phenomena of rising groundwater, critically shallow groundwater, and increasing salinity. And what we found was that we can expect damage to roadway, which we think is a piece of surface infrastructure, but there's layers that go beneath the ground. And then to our piping networks, including for our drinking water, our storm drainage, and our sewage infrastructure. And then for our buildings, what we get is corrosion of the materials that make up those buildings, and then pressure-induced heave from the tide, raising and lowering that groundwater. So I'll take you just quickly through our modeling methods for how we look at drainage backflow and how we look at groundwater inundation. And so first, for our drainage layers, we take the approach that's very, very similar to what like NOAA uses, what we use for our past direct marine flooding, and that's bathtub modeling. So it's a pretty simple concept where you look at the elevation below whatever amount of sea level rise you're thinking about. And so here, this is the NOAA sea level rise viewer. They're looking at 5 feet sea level rise. And so basically anything below 5 feet is highlighted. And that's pretty much as simple as it gets. But we add a little bit more complexity for our drainage infrastructure. So we look at areas below that elevation and areas sufficiently connected to drainage infrastructure. And so that will give us locations of drainage infrastructure doing that double whammy thing where it's not actively draining stormwater and it's causing that additional bit of flooding. And then in the dark blue, that shows areas below that elevation of sea level rise we're thinking about and superficially connected to that failed drainage. And so we simulate that in 1 foot increments of sea level rise, all the way up to 10 feet. And so this information is really helpful for folks who oversee planning for drainage and currently manage the workings of that drainage system. And this is a very simplified way of doing that modeling. And Chloe O'Barrett is going to talk next about our more robust way that we do this modeling. And then there's groundwater inundation modeling. And what we do here is we take robust models that were put together by the USGS that specifically look at drinking water resources. And those are mainly in the volcanic aquifer. But the aquifer that we're worried about and we're thinking about is the coastal aquifer, which is adjacent. And so we have to redesign these models. First, by mining data from places like the Department of Health leaky underground storage tank records that include information on site-specific geology and site-specific groundwater levels. In some cases, we install our own wells to look at how the tides and rainfall influence groundwater in site-specific areas. And then we populate our modeling domain with this information. We populate it with additional geologic data from the USGS, with recharge data from the USGS that represents rainfall, as well as water coming from the spring-fed systems from the volcanic aquifer down to the coastal aquifer. And then we run our simulations considering different levels of the sea level rise. And what our models give us, this is the windward side of Oahu, and what this represents is the model simulation of groundwater elevations above sea level. And then we compare that to a digital elevation. And with that, we're able to see where groundwater is expected to be emergent, and that's the light blue and dark blue. That represents kind of like flooding or inundation of less than or more than a meter. And then in the light yellow, that represents critically shallow groundwater. So that's the level, that's at 1.5 meters or about 5 feet of space between the ground surface and the water table. And from our work in putting together our review paper, we found that that elevation is the one that kind of really triggers damage to our underground infrastructure. And then the more vivid yellow, that shows where groundwater is likely to become emergent with like a rainfall event. So it's just barely below the surface. So that threshold is 0.3 meters or about a foot below the ground surface. It's really close to being emergent. And then we simulate 1 foot increments of sea level rise. So this data is really important for infrastructure managers in charge of that underground or roadway infrastructure. And yeah, very dramatic results, as Sock said. So yeah, that's your whirlwind tour through how we do our drainage and groundwater inundation modeling. And that's it for me. Chloe's up next.
Try to keep clicking it okay.
Oh, it's only on the screen. It doesn't exhibit it there. No. It's not on the screen.
Don't worry about it.
Okay, so as, oh, it is off. As Shelley mentioned, we are also doing a more rigorous modeling study into specifically how the storm drain backflow component is exacerbating flooding in Waikiki. So you've heard there's numerous effects of flooding to coastal urban areas, but less studied have been this combination of when we have precipitation from storm events in conjunction with storm drain backflow, and this does really compound the effects of flooding. So as you've heard, climate change is reducing storm drainage capacity with higher sea levels, groundwater levels, and tides. That existing base level of water in the storm drains is going to be higher, such that when we have a rain event, we're more soon going to see that backflow, which can be hazardous to transportation and infrastructure. And so our goals with this project are to collect some real data on those water levels, and then use that data to model current and future sea level rise steps. So the model we use for this study is PC-SWIM. It runs on a software developed by the EPA. It's been used for similar drainage studies. And it's a good candidate for this kind of work because it does incorporate the hydrology, as Kayla's model has done. And then it also has this hydraulic side that incorporates the actual storm drainage network. And so it takes inputs of rain events and tidal boundary conditions, and then shows numerous outputs of how we can represent that flooding, which I'll talk about later in my results. So this is what the actual storm drainage network in Waikiki looks like. The nodes or the blue dots are those inlet points. The conduits or the yellow lines are the pipes themselves. And then the outfalls or outlet points are the red triangles. And so you'll notice that actually the majority of Waikiki does drain to the Alawai. And the Alawai is also responsible for receiving all the rainwater inputs from the Manoa Palolo stream. So that in itself can be a source of some of that plugging and backflow. And so to collect the actual storm water level data, we install these pressure transducers in the storm drains. So there's currently 10 of them in the Waikiki storm drain network. They sit at the bottom of the drain and collect water level data in 5-minute intervals. So for our current results, we're using a 57-day data set from February to April of 2023. And this is just an example from the Seaside Alawai transducer. So this is the water level over time. And our results capture the peak values during this simulation. So this occurs during this peak here. And if we expand this, what you're looking at is a rain event that occurred over 3 hours. It was about 2.8 inches of rainfall, and this is a 5-year recurrence interval rain event. So a smaller rain event, something we might expect to see fairly frequently. It also occurred during fairly average tidal conditions, right around mean sea level. And then to generate the tidal inputs, we also use our transducer data as the boundary conditions for the outfalls. And then when we want to apply sea level rise, we can simply add 1, 2, or 3 feet to these data. So as you've seen, this is the sea level rise projections. We expect to see 1 foot of sea level rise. This is the intermediate scenario, 1 foot by 2050, 2 feet by 2060, and 3 feet by 2070. And then if we want to use the intermediate high scenario, these numbers are shifted forward by about a decade. So looking at my results, this is specifically how the storm drainage infrastructure will perform under this simulation. So when the conduits or the pipes are shaded in blue, this indicates that they're full of water for greater than 50% of the simulation time. And so this is a proxy for capacity limitation. And then any outfalls denoted by a blue triangle are experiencing that stage 1 failure that Shelley just mentioned. And so even during present day conditions with no sea level rise applied, we see that 74% of outfalls are already at stage 1 failure. And then we can start to use this data to make recommendations for management. So for example, the Miami Beach area uses pump stations to manually drain portions of their city, and they experience very similar flooding impacts. So we could look at a target location that could be a good candidate for this kind of management. And then looking at the nodes or the inlet points, similar to Shelley's gradient scheme, when we see yellow nodes, this means that the maximum water level came within 5 centimeters of the surface. Orange indicates that the water reached the surface, and red, the water exceeded the surface or overflowed. And we see low levels of this during present conditions. Then when we apply a foot of sea level rise, 90% of outfalls are at stage 1 failure, and 15% of the conduits are at reduced capacity. And we now see 9% of nodes overflowing, 10% at capacity, and 2% nearing capacity. And again, this is useful for property managers so they can understand where we might expect to see this flooding first and how they might need to adapt their properties to account for additional flooding. Looking at 2 feet of sea level rise, 95% of outfalls are at stage 1 failure, and 35% of conduits are at reduced capacity. And then we see 35% of nodes overflowing, 16% at capacity, and 4 nearing capacity. And then lastly, at 3 feet of sea level rise, 97% of outfalls are at stage 1 failure, and 68% of conduits are at reduced capacity. We have 80% of nodes overflowing, 13% at capacity, and 1% nearing capacity. So this is 94% of the system totally compromised. And so this work, we know that sea level rise and high tides are already causing drainage failure, but this shows that this lack of capacity will continue to worsen compound flooding in the future. And then some future directions for this study specifically, we can also adapt this model to specific sea level rise scenarios or design storms as necessary. And then we're also looking to incorporate a 2D component to see the surface extent of flooding. And then this just does confirm the need for management to address current and future flood risk to Waikiki area. So thank you very much. Yeah, we'll hear from Anna and Rochelle next.
Can you guys hear me?
Yes.
Hey, hi, my name is Anna Mickelson, and I'll be sharing some of our work on coastal monitoring and modeling with my colleague Rochelle Moskvicek. And the CRC here has a long history of monitoring and modeling coastal erosion to better understand the areas that are at risk today and how that changes under rising sea levels. So the current iteration of our coastal erosion modeling is called Cosmos Coast, which Rochelle will introduce. And a critical input into this model is a history of past shoreline change for the particular beach that we're modeling. So it's really important to understand the particular dynamics of that coastline to best inform future projections. So to underline this, here's an example of some of our past modeling in Hauula, which is a chronically eroding beach. And you can see as we project that erosion into the future, it accelerates. On the other hand, if we look at a beach here in Kailua, one of the few historically accreting beaches, that accretion under the modeling will continue for some time until the sea levels rise enough to force a landward migration or erosion. So this is just to highlight the importance of having a really good, accurate, place-based information for each of these particular shorelines that we're modeling. And so that brings me to our current work. We are trying to monitor all coastal sandy areas in the state of Hawaii. And so to do this at scale, we are looking to use the available satellite images, the large available satellite images combined with new computer vision and AI methods to essentially automate the contouring of the shoreline positions for all of these images for every single sandy beach here. And that brings us from having sort of a data point per decade to now having a data point every month, and more recently, nearly every day. So to give you a brief idea of what sort of imagery we're looking at, it's a mix of publicly available satellite images from Landsat and Sentinel. These are quite coarse, but they date back all the way to the 1990s, so they give us crucial information over the last 30 or so years. More recently, we've been using PlanetScope, which is a proprietary satellite company that aims to map the entire Earth every day at a resolution of 3 meters. So that brings in a really nice high temporal and spatial resolution to our data set. And then we also have an in-house sort of drone monitoring program that we're using consistently to benchmark and accuracy assess the shorelines that we're deriving from our satellite images. And there's a lot that goes on sort of under the hood, but a general framework is first to classify or segment the image into water and land. And from there, we can contour the shoreline. And on top of that contour shoreline, we can intersect it with digital transects. These are spaced 20 meters apart. And if you're familiar with the coastal change viewer, these are sort of the similar transects. So I want to just jump into a few results. Here's a snippet of the North Shore of Oahu. And along each of these transects, we then have a history of shoreline positions over the last, here's a snippet of over the last 23 years. Each of these dots is an individual image, so the data is quite noisy, but there's so much of it that it actually enables us to discern patterns that we haven't really been able to see before at this scale. So we can look at things like the monthly mean shoreline position in the black line, where we start to see that seasonal trend. And if we model this seasonality, we can actually look at, for this particular beach, what time throughout the year is this shoreline historically most eroded. And for this particular case, it's around mid-January, which is sort of what we'd expect for the North Shore. Here we've color-coded the transect by the season where they're most eroded. And again, as we'd expect, blue indicates the winter months, so much of these beach segments are most eroded during the winter. And we can also look at the long-term change rates, with darker reds here indicating stronger erosion. So we see quite a lot of erosion here in this section of the North Shore. If we zoom out and look at the whole state, here's a snippet of those same figures with orange indicating a lot of the south-facing beaches being narrowest during the summer months, and the north-facing beaches being narrowest during the winter months. And looking at the long-term change rates, we see a lot of erosion, but also a lot of information and a lot of variability. And all of this information we can bring with us into the Cosmos Coast model, which helps us best project future erosion rates for each of these shoreline segments. So with that, I'm going to pass it to my colleague, Rochelle, who will introduce this model.
Thanks, Anna. Hopefully you can see me. I'm on Zoom World. My name is Rochelle. It's nice to meet everyone. And yeah, so I will be talking about how the shoreline monitoring that Anna was speaking about earlier is very important, and it is used to inform the new model that we use to estimate future shoreline change in Hawaii. And this model is called Cosmos Coast, and I'll walk through how it works and then show some results for the North Shore of Oahu. See if I can control the screen. I assume it's not changing, right?
Yeah, I'll change it for you, sorry. Technical difficulty.
No problem. Click again. And again. Thanks, Anna. So I'll start with how we use the satellite observations that Anna was speaking about within this model. So here's an image from Sunset Beach on the North Shore of Oahu. And using the methods we talked about earlier, we can find an approximate shoreline contour for this beach. Next. Next. This line intersects with the transects that we have for the model to find distances that the model then assimilates into its predictions. Next. And here, looking at this graph, we are looking at total shoreline position as predicted from the model. So we have time on the x-axis, and it goes from about 1990 to 2150. And the first part of this graph, from 1990 to present or 2022, this is when the model is tracking the satellite imagery. Next. Sorry, click one more time. Thank you. The blue dots here are the shoreline positions found on a single transect, and the red line is the adjusted shoreline position. And so this model is taking in all of this information, and then after present day, it continues to predict the shoreline position into the future, such as until 2150. Next. I'll go briefly through the Cosmos modeling equation. This model was originally created by Sean Batusek, who now works for the USGS. I believe Sean is on this call as well. Next. The model takes in two inputs, a 4-year wave timecast time series and sea level rise projections. And each color that you see inside of this big mathy equation is a different shoreline process, and they work at different time scales. So we have long-term components. We have first in a longshore transport component from waves. We have cross-shore migration due to sea level rise, and we have a linear change rate term that accounts for other sources of sinks. And something special about this model is that this longshore term provides a theory to understand how the sand moves across a beach, which is something not previously used in our past erosion modeling. Next. And then in the short term, we also have the cross-shore equilibrium wave term that can account for seasonal changes and an uncertainty term. Next. And all of these add up to get the change in shoreline distance along a given transect. Next. And then we project this line backwards to the certified shoreline, which is often classified as the vegetation line, and is also defined as the upper reaches of the wash of the waves of the highest tide. And so everything seaward of this line is assumed to be within the potential erosion hazard zone. Next. So now I'll walk through some results for Sunset Beach under the intermediate high sea level rise scenario. This base photo is from 2019, and I'm showing a digitized present vegetation line from 2022. Next. And as Anna clicks forward through the sea level rise feet projections, we go all the way up to 6 feet. And we're actually hoping to go all the way up to 10 feet, at least under the intermediate high scenario. And we plan to forecast these erosion hazard zones at the 80th percentile, meaning that there is an 80% probability that the land impacted by erosion will be within this exposure zone at a particular time. And next. we have these potential hazard lines for nearly all of Oahu, for both the intermediate and intermediate high scenarios. And our next steps are to start moving on to the other islands. We're starting with Kauai first. Next. And we're going to, of course, continue to work and improve our satellite processing and gather more data. Next. And we're also hoping to publish a paper explaining how this Cosmos Coast model is different and hopefully improves upon the previous modeling that was done by Tiffany Anderson back in 2018. Next. Yeah, and with that, I'll pass it on.
Great, thank you. Okay. Oh, okay, so yeah. Yeah. Okay. All right. So just unshare on the unshare. Yeah, unshare. Yes.
Hello, everyone. My name is Christian McDonald. I'm a geospatial analyst in the Climate Resilience Collaborative. I'm going to be presenting with my colleague, Aloha Kapono, who is also a geospatial analyst. We're going to be talking about the Hawaii Shoreline Study web map. So, what is the Historical Shoreline Project? Well, it's an ongoing project that's been going on for nearly 2 decades. And the goal of this study is to provide scientific and empirical data to the public so that they can better understand coastal change over time, whether beaches or coastlines are eroding or accreting, and to identify areas that may be exposed to erosion and rising sea levels in the future. So they say a picture is worth 1,000 words, and this is probably worth more. These are the kinds of issues that we're facing. This is in Paumalu, on the north shore of Oahu. This is between Sunset Beach and Rocky Point. But given that we've developed along the coastline, we've pinned in beaches, we've bulldozed dune systems, so that the beach can no longer call upon that sand. We're experiencing pretty severe erosion in many places around the state. And this is only expected to be exacerbated given sea level rise. And you can check out this study by Dr. Tiffany Anderson and all in the Journal of Natural Hazards if you're interested in learning more. So this study starts with imagery. So we have aerial photos that go back to the early 1900s, primarily crewed aircraft, but lately we've been incorporating satellite imagery and drone imagery. So you can see examples of that here. This is for Punaluu on Oahu. The drone imagery is particularly exciting because using photogrammetry techniques, we can generate surface models so that we can do sea level rise analysis or hydrological modeling. But for this particular project, we're mostly interested in the two-dimensional orthomosaics. And it takes quite a bit of processing to get this imagery sort of ready to go. Firstly, we have to do a geometric correction of the images. So this means we have a reference image, the best available reference images that we have, and we have a target image. For example, this is from 2022 NRCS data on the south shore of Kauai. And we find control points. So these are stable reference points that exist across the 2 different data sets. So if we zoom in, things that we tend to use, features that we tend to use are tennis courts, basketball courts, manhole covers, pool corners, driveways, road markings, those sorts of things. And so we have all these control points so that we can align the images perfectly so that we're comparing apples to apples.
Next, we have to digitize some features, namely the vegetation line. This functions as our landward boundary of the beach and is identified using trees, bushes, shrubs, grasses, etc. And the low water mark. And this serves as our sort of seaward boundary of the sandy beach, a shoreline proxy that's defined as the base of the foreshore or the beach toe. So I have a little video that kind of pieces everything together here. So this is Kualoa on the east side of Oahu. So like I said, we have aerial photos that go back to the early 1900s. Here we have our low water mark depicted in blue and our vegetation line depicted in green. And we're working forward in time. And you can see that this area has changed quite a bit over the last century. Here's some drone imagery that we've been incorporating. You can see the high resolution. Now we have our low watermarks and vegetation lines overlaid on top of each other. And from here, we have an offshore baseline from which we cast shore normal transects. These are perpendicular to the beach. And with the intersections of the low watermarks, we can then do a linear regression and find a shoreline change rate. So this particular area is eroding at 3.2 feet per year. And then given sea level rise projections, we can forecast this into the future to develop future shoreline hazard zones for the years 2030, 2050, 2075, and 2100. So these are areas that will be potentially exposed to erosion in the future. And with that, I will pass it over to Aloha. Stop sharing. I think you might be muted.
Good morning, everybody. Can you hear me all right?
Yes. Yep.
Okay, wonderful. My name is Aloha Kapono, and today I will be walking you through our Hawaii Shoreline Study web map. And so in order to get to this resource, you can navigate to our website here, and it's found in our resources tab, and it will be our very first item. So as you go ahead and click through that, you'll get to our overview page. And so this is our disclaimer box, and it's important to read because it explains the appropriate use of this data, and our information is here to improve our understanding and our awareness of shoreline change. So you can go ahead and press I agree. And then here we have our default extent of the Hawaii Islands. We have data that covers Kauai, Oahu, and Maui. And today we're just going to go and look at a study area on Oahu. Specifically the Ka'a'awa area in the moku of Ko'olauloa. And so this area has sandy calcareous beaches, there's seawalls and homes along the shoreline. If I want to go ahead and zoom into this study area, this area of interest, I'll go ahead and click the zoom in, which is these icons that are listed on the left side. We have different icon functions that are listed. So as I go ahead and zoom in a little bit more, you'll see these red and blue lines, and the lines we call transects. They show areas of erosion and accretion. Again, as you zoom in a little bit further, these values and numbers are associated with each transect. Taking a look at our main toolbox and all the icons on the bottom right-hand side, you can do different things. So you can check out the legend. You have your layer list that allows you to click on and off the different layers. You can select your base map, measure features and lines. You can share this data and information, and as well as print. So taking a look at one of the layers, which is mosaic footprint, I'm interested in this Ka'a'awa area, and I want to know what is the most recent mosaic drone-derived imagery that we have available. So if I click in this general area, this pop-up configure will appear. And then I can swift through and look at other years of data. But I want to look at 2021. So we'll go ahead I maximize this view and I can see the date that it was collected. I can look at the source file name for this, and I can also download it immediately right here. Again, here is our Hawaii low water mark, and these are all the lines for all the various years of imagery that we have. Selecting each feature polyline, you can see what year this is associated with. Maximizing it, you can definitely look at all of the information here and what mosaic that it was digitized from. Similarly to the vegetation line, you can click it on it and see what associated mosaic it was digitized from. And so here are our historical transects, as I mentioned earlier. So each one of these transects has a linear regression plot associated with it. And you can take a look and maximize and see, okay, this area is showing definite signs of erosion. Now, conversely, here is Kahana, which is a little north of the Ka'a'awa area. And I am looking at this transect number 6, and I see, hey, this area is actually accreting. And so these hazard zones are modeled on how shorelines have changed in the past and combined with predictions about rising sea levels. And these marked areas are places that could be at risk of full energy waves and trade winds of rising sea levels in the future. So this can tell us which pieces of land will be affected and gives us a good idea of places that might be at risk. Now, these are future polygons of each projection that in the future. Now we are also updating these shorelines with 2022 and 2023 data. So please check us out on our website, and this is all open access data. And here's our contact information. So if you have any questions, please let us know.
There was a question in the chat, just asking if you could add TMK layers to the shoreline change web map.
Yeah, that's definitely a possibility. That's a great idea, and we can definitely do that. Great question. Thank you.
All right, my name is Juliet Budge, and my background is in climate change and human migration. And for the CRC group, I actually do some grant writing and then also do some other research. But today I'm going to be talking to you, kind of wrapping up all the things we've already been exposed to, which is a lot of modeling. And going to be talking about kind of the vision for the CRC and expanding beyond just our exposure modeling that you've seen. So the CRC works to project future climate impacts and assist in climate resilient development for coastal communities in the Pacific. So to date, we've focused mostly on Oahu, but also outer islands. And actually, we have a project right now that we're going to be working in Ponape and Yap. So we're moving kind of beyond just Hawaii. But when we focus on the state, we are embarking on a process of moku by moku doing resiliency planning. So this modeling that you've seen mostly has been funded by the Office of Naval Research to develop kind of all these advanced modeling tools. And we are going to first be applying these tools in Ko'olaupoko in partnership with the Office of Local Defense and Community Cooperation. This is part of the Department of Defense, but it's really a grant that's interested in things outside of the fence line. And we're going to be doing this in partnership with the Resilience Office at the City and County of Honolulu, and also local engineering firm Brown and Caldwell, and a consultant group called One World, One Water. And in addition to all of the folks on the team that I just mentioned, we're also having 2 committees. One of them is a steering committee, so more interested in like the policy side. and then a technical committee of people that work in local government or community members themselves, neighborhood board members, folks like that, who can really give insight on topical matters. So Ko'ola Poko, as I mentioned, this is actually an image that Christian, I think, took down looking towards Kaneohe Bay of the region. And a lot of the modeling you've already been exposed to today, but sea level rise is kind of top on our list. That's really historically what we've been kind of experts in. This is an image of Kailua Beach and the ironwoods getting eroded away. And then heat, this is a new thing in our toolbox. While the state has had one heat modeling kind of mapping, I think they did it in 2021. Coming up this summer, we're going to be doing it again, a campaign where we really understand what's happening in our communities with heat. And a lot of the architecture on the island wasn't designed to deal with rising levels of heat. So it's really something that impacts people now in their daily lives and is important to be able to perceive. Next is flooding. I think this picture is actually in Hauula, but as you saw from a lot of our discussions today, flooding is a pretty major issue that's going to be only increasing as we look into the future. Wildfires, I don't think I need to really discuss this because it's been so omnipresent in our lives lately, but we can actually predict wildfires. What we call it is landscape. What is your word, Chip? Landscape ignition. So really looking at what in an environment might lend itself more to wildfires than others. Sensitive infrastructure, Shelley and Chloe discussed this. This is an image, I think, that's pretty typical of exposure of the road from water. Our pipes are exposed. There's lots of things in addition to our transportation systems that we need to be considering. So we're laying that into our maps in addition with all the modeling that you've seen. And then also considering kind of demographic aspects, so social vulnerabilities. And we collect all this modeling information and then put it into more like a theoretical framework, I guess you could say, where we look at sensitivity, which are characteristics that lead to harmful response to a dispersed disturbance, and then also exposure, which is the likelihood of a disturbance occurring. And that's what we call vulnerability, which is this exposure and sensitivity combined. And balancing that out is adaptive capacity. So the potential for systems to adjust to impacts from shocks or stressors. And our group, the way we approach this kind of issue is modeling, which you've seen, really advanced modeling of climate, sea level rise impacts, and then mapping. You got to see Chip walk through our viewer a little bit and hear Matt talk and Kyle about the mapping. So we do all of the kind of mapping of these physical aspects of sea level rise and heat, and then we're also layering in those infrastructure level layers, socio-demographics, and land use layers. And communication, so these viewers are really considered, they're maximized to make it a user experience that is more accessible than kind of just putting a big report in somebody's lap, but really making it something that can be interactive and maybe even enjoyable for some folks. And then community is an aspect that's really important to our group. We're really looking towards having more reciprocal relationships, inclusive and mutually beneficial research. So that's the target kind of what we're working towards at the CRC. And while you've heard from a lot of folks today that work in our group, you haven't heard from everybody. These are faces of everybody on our team. We even might have some people that aren't on there, but the important thing is that we come from a lot of different backgrounds. And I think that makes us really unique in a way that we are truly collaborative. Some folks are from architecture, urban planning, a lot of the geosciences. So I think that's an interesting aspect to the work we do. And we really are focused on making the community more resilient. And it's been really nice to have all of you here from kind of around the table. And yeah, thanks for joining us. So that's all I have for today. And I'll hand it back over to Chip.
So thanks, everybody. You see there are a lot of people involved in this. 90% of them are soft money researchers. And so a big effort is the funding that comes from all the counties, state agencies, and federal agencies. We've been supported for decades, and putting together all of this data has been a real team effort. I want to wrap things up at this point, but